I first heard the word affordance in a sports coaching lecture at university. The teacher asked us what the table afforded, which I remember thinking was the weirdest question. When you search for a definition of affordance online, you'll see things like a use or purpose a thing can have, an implicit understanding of how to interact with something, maybe a quality or property of an object that defines its uses. Most definitions about an object affording something. But my lecturer kept asking us over and over again, what else? What else? Like, you can put stuff on a table, sit on a table, stand on a table, but we quickly ran out of ideas until he said, what about afford? And that made no sense until he explained what he meant. What if we pretended if it was afford? When I was younger, I would put a bedsheet over the table and pretend it was a tent or a fort or a hideout, the table affording more behaviours than we initially thought. In the ecological approach, instead of perceiving lower order variables like height, width and angle, the argument is that we perceive higher order variables referred to as affordances, the opportunities for behaviour, a table being a fort. But importantly, opportunities mean they could happen, but haven't necessarily happened yet. And so we are perceiving whether, when and how we could behave before we do it. Perceiving a possible future, not really predicting a future, which is where the ecological approach differs from traditional approaches. The main difference is the assumption of local linear causality. I think most people would say the past impacts the present, and the present could impact the future, but not many would say the future impacts the present. The future is unknown, but we perceive whether, when and how to move to catch a ball. We perceive whether, when and how to move to stop a car we are driving. We perceive the future all of the time. It isn't useful to be aware we can stop a car after we've hit something or after we have stopped. It is more useful to perceive the possibility before we attempt it. That doesn't mean perceiving affordances is always accurate. It's not, but the argument is that we must perceive possible and impossible futures. However, you are probably thinking that, well, the past are stored memories, and the future is your imagination, those ideas being very different from perception. Well, the argument here is that memory and imagination are part of perceiving the world, perceivers perceiving things, and the environment being perceived. But this is where primary and secondary properties are used in descriptions. Primary properties of objects don't need an observer. Things like size, weight, shape, they won't change. They are objective properties. Secondary properties require an observer. Things like colour, taste, texture, these are subjective properties. But the problem here is that affordances need to be either primary or secondary. They can't really be both. Affordances can't be objective and subjective at the same time, but they are. Like the table as a fort example, the height is objective, but the use as a fort is subjective. And so if we use the fifth assumption from the ecological approach, where the organism or animal environment system is the fundamental unit of analysis, we don't need to separate the perceiver from the environment. Now, affordances are more like friction. Friction is created when two objects contact with one another. Friction then emerging from the relationship between the two objects. Affordances emerging from the relationship between the organism and its environment. But an organism's action capabilities and the environmental properties will change that relationship. Some researchers calling action capabilities effectivities, but I think they mean the same thing. The size, shape, mass, strength, dexterity, and skill of an organism, like how it moves or how it moves objects in the world, will differ. Each species will have different action capabilities, flying, swimming, walking, but then animals in the same species will be different, jumping higher, running faster. But then, even the same animal will have different capabilities in different situations. A standing start or a run-up for a jump. And these are important because species, animals, and situation differences guide our behaviour, sometimes for survival. Prey perceiving affordances of their predators to escape and survive. Perceiving the differences within species and the situation guides behaviour. Although Euclidean geometry and Newtonian mathematics are great for describing objective properties, primary properties, they aren't great with subjective properties, secondary properties, which, as discussed, affordances partially are. This is where some people have called for an ecological physics or ecological geometry, but affordances don't just rely on one property of the organism and one property of the environment. There is most likely multiple properties of both for the affordance to emerge. For a surface to be stand-onable, it needs to be flat enough relative to the animal's ability to balance, but also big enough relative to the animal's size, and rigid enough relative to the animal's mass, among many other things. Each one is necessary, but none of them alone are sufficient. Which brings us to the meaning in each organism's experience, an object having a different meaning in a different situation to a different organism. Meanings are often described as being both subjective and internal, often as something created internally and then placed externally onto an object. However, in the ecological approach, meaning isn't seen as subjective or internal, nor objective or external. Meanings emerging between the relationship of the organism and environment, just like affordances. And that is deliberate because affordances are activity-specific meanings of the environment. Affordances are meaningful and perceived, not created or represented. I just want to emphasize that meanings can be perceived. Which begs the question, how do we study affordances? James Gibson first described the concept in 1966, developing it further in 1979, but it wasn't until 1984 that Bill Warren measured the idea when climbing stairs. The idea was that it isn't the height of the step that is important, but the height's relation to the leg length of the person. Bill tested this preventing different modes of getting up the stairs, like climbing or using a rope or other tools, and he calculated a ratio for the height and leg length under ideal circumstances, using a biomechanical model. The ratio was called critical pi, and it came out to be 0.88. So the stair height was 88% of a person's leg length, which obviously means taller people will be able to step on taller steps. But the hypothesis was that the relationship, the ratio, between the stair height and the leg length would be similar, if not the same, irrespective of the person's height. So in this first experiment, there were two groups. A tall group with an average of 190 centimetres or 6 foot 3 inches, then a smaller group with an average of 164 centimetres or 5 foot 4 inches. Each group was shown images of stairs. There were 5 different heights, ranging from 51 centimetres or 20 inches, 102 centimetres or 40 inches, in 13 or 5-inch increments. For context, the average US home stairway is 18 centimetres or 7 inches per step. Each person saw the stairs twice in random orders, and they were asked to say yes or no to whether they think they could step onto the stairs. The yes responses were plotted on a graph. As expected, as the height increased, more people said no. And as expected, the taller group said no at the higher heights than the shorter group. Bill Warren then looked for perceptual boundaries, when people perceived the stairs to be step-onable or not. So if we take the 50% line and go down to the height, the shorter group were at a step height of 67 centimetres, about 26 inches, but the taller group were at 81 centimetres, about 32 inches. Not really surprising. But then he divided the step height by the leg length, and you can see the lines look similar. Both groups perceived the stairs as step-onable in the same way. This is huge for at least 2 reasons. First, it shows affordances are body scaled. It depends on the leg length and the stair height. But second, this ratio isn't just similar, but it was identical to the critical pi value of 0.88 he calculated with the biomechanical model. Warren then followed this up with 2 more experiments, stepping not just relying on a person's ability to get their foot high enough, but also the ability to transfer their mass from the lower foot to the higher foot, the person needing to do something to step up. This adds a measure of effort. Some steps are requiring more effort than others. In the second experiment, Warren measured oxygen consumption, just like they do in modern sports science, to get a measure of effort. Unsurprisingly, the optimal height for shorter people was shorter than the taller people, with the optimal pi value coming out at 0.26. So the most efficient height was about 25% of leg length. However, in the third experiment, instead of stepping, the participants were shown images, like in the first one. And instead of optimal pi, this was termed perceived optimal pi. The participants were asked to rate how comfortable each step would be on a scale of 1 to 7 to step on. And the result came out about the same, 0.25 or 25% of leg length. These 3 experiments together support the idea we can perceive how climbable something is, but also how effortful or efficient it would be to climb a step. And so we could say perception is action scaled as well as body scaled. But how do we then perceive these affordances? Patterns in structured energy. I will go into more detail about what that means in future videos, but the way I think about this is picking an energy source like a light or a smell or a sound and following that energy everywhere. So for my light, the source, the light bounces around and travels all over, just like all of the other light sources. Smells from the candles next door, or me after playing sport, again, spread around in an array, the space. All of the energy being uniquely structured by the environment. Light reflecting, mirroring, and being absorbed by me and my wallpaper and other objects in my room. Things smell stronger when you are closer to the source, just like a light is brighter when you are closer to the source. So the substance and surface properties, how flat my wall is, lawfully structure the energy, the light energy. But then I move, so my point of observation changes over time, just like all other organisms. This will depend on how we all move and move other objects in the world. Taller people having a different point of view to me, and then other animals detecting the energy, very different from me. But the structured energy from the environment relating to the organism's observation point is information about affordances. These points together make perception a lawful process. Perception ought to work the same regardless of light, chemical, or pressure on the skin. Not exactly the same, but comparable, analogous. Which means the same affordance ought to be perceivable by multiple perceptual modes. Our senses, multiple senses perceiving the same affordance. Burton in 1992 tested this by asking people to stand at the edge and perceive if they could step over different sized gaps. As expected, people using visual perception were good at this, working out if their leg length was long enough to step over the gap. But then people were asked to do the exact same thing blindfolded, holding a wooden rod in their hand, much like how a visually impaired person uses objects to move around the world. And despite these people having limited experience with using wooden rods to perceive a gap, they could do it. Albeit more cautious, but they could do it. So they perceived the affordance both through visual perception, but also haptic or physical perception. The vibrations and position from the hand on the rod. You could say they used a mental model or mental image and did lots of calculations and interpretations to work out if they could cross, but this must be true for other organisms as well. Toads, snakes, and all other organisms that cross gaps relative to their body size and how they move through the world can do this. Do they all create mental models and do higher order mathematics to perceive if they could cross a gap? The ecological approach says no, but they don't need to. animals perceive affordances, whether, when, and how to act relative to the dynamic constraints in the situation. Just the objects available, the capabilities available, with plenty of studies supporting these ideas, some studies adding objects to animals or people to see how that impacts their decisions to move. All organisms' ability to perceive affordances improving with practice, learning through experience, but crucially, affordances are being perceived directly, detecting information from energy sources about the affordance, not perceiving properties of the organism and environment and then doing calculations. So step height is X value, which is smaller than 88% of my leg length, which is Y value. That means I can climb on the step. The research doesn't support those ideas. I will share more articles about this in the future, so subscribe for that if you're interested. But this is not to say isolated properties can't be perceived. They obviously can, but they aren't the main content of organism perceptual experiences. Affordances are. And perceiving affordances doesn't necessarily require perceiving isolated properties. This is significant when we consider developing behaviour and designing practice for that learning. Isolated practice resulting in different, oftentimes drastically different affordances emerging than the situation they are training for. I spoke more about that in this video over here.